Thank you very much. Good afternoon and welcome. It's quite interesting to be speaking on this stage rather than listening as I did many times many years ago. My subject today is really about engineers and engineering and particularly how things that we take for granted and seem very simple can be quite amazing underneath. I guess I want to start with a quote that some of you may have seen before from a science fiction author called Arthur C. Clarke, who many years ago said that any sufficiently advanced technology is indistinguishable from magic. To those of us who were brought up in the day before computers and internet and wireless and so on and so forth, to be honest, an awful lot of what we can do today seems pretty much like magic. The idea that you can, well, to be honest, stand here and change the picture behind you, that's pretty magic to me. But it's quite straightforward, and of course it's technology driven by engineers. I didn't want to do the normal sort of talk about what I'm interested in, so I thought, what better way to do this than to ask you. So the shelves will know that a week or so ago, I sent you a very quick survey to ask you about some things that you might think in believe. So you've helped me write this talk. And the first thing I asked you were some questions to kind of try and establish what engineering is and what part engineering plays in our world. So I gave you 10 examples of what I consider to be quite great achievements, things that make a big difference to our world. Things like the pyramids or the road network, that's the highest bridge in the world, which is in China, by the way. Discovering the origins of the universe and studying all of those things. And I asked you, across all of these things, which did you think was the greatest achievement? And I guess it's quite interesting to think about the different groups that I've asked this question to and the different answers that I got. So, the first result from the survey, perhaps to my surprise, what you guys told me was that in your mind, the internet is the greatest achievement that has been done to date. Second place, understanding DNA, and in third place, the moon landings. Now, I guess if I'd asked a different period of a different group of people the same question in a different way, they might have come to a quite different answer. But it's quite interesting to sort of think about those great achievements, those different things that have gone on. Interestingly, and we'll come back to this, none of you thought television was a great achievement at all, so I'm sure that as you go back to your houses later on, none of you are going to be asking to watch television. When mums and dads, when they come home on the holidays, just remember, they think that television is not a great achievement, so let's get rid of it, okay? But more importantly, I then asked you, which of these 10 things did engineers contribute to? And you were allowed to tick as many as you liked. Okay? So, the results for this actually surprised me quite a lot. Because, okay, at the top of the list we've got global road and railway network and the moon landings. But even on those, the road and railway network, only 75% of you thought that engineers were involved in those. And the moon landings, only 2/3 of you thought that engineers were involved in the moon landings. Which is quite interesting, because I'm not quite sure how you get to the moon without an engineer to help you actually design and build the rocket and all the rest of it. So, but there's a message here. Something that I was actually sort of trying to get across is that actually every single one of those 10 achievements, and you can make another list of 10 and another list of 10, and we were making that list. There's nothing magic about those 10, they're just 10 things. But every single one of those, there are engineers playing a substantial and significant part in it. And I kind of wanted to explore one of those in a little bit more detail, just to sort of illustrate the point. So the one that you guys put at the bottom of the list, running the 100 metres in 9.58 seconds. Now, of course, the first thing that you need if you want to run the 100 metres in 9.58 seconds is a big Jamaican chap who can run very fast called Usain Bolt. So it's kind of quite helpful to have some biological input, shall we say, to that. But actually, there's a lot of other things that you need if you're going to run 100 metres in 9.58 seconds. So what are those? Well, the first thing is you need the right track. If you trace back through 100-metre world records, then 100 years ago, it was about 10.1 seconds, and it's kind of gone down, 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 and down. But one of the big factors there is the move to modern tracks and modern track technology, and the ability to make a track that is fast to run on. The design of that track surface to have the right combination of give and propulsion and friction and all of those things. So there's some real engineering in designing the track, and some real engineering in constructing the track. And of course, if you're going to run very fast as well, you need the right shoes. And anybody who's been out to buy trainers recently will know that if you want the right shoes to run at that kind of pace, then you need real technology to have light shoes, strong shoes, the right grip, etc., etc. So there's some pretty deep engineering in the shoes. But there's more than that, because, of course, I said it was 9.58 seconds, not 9.57, not 9.56. You need some pretty accurate timekeeping technology. To illustrate it, I've got a picture of a stopwatch, but actually, of course, a stopwatch is totally inadequate for timing to 100th of a second. You need some quite complex timekeeping technology to trigger the start and to trigger the finish. So measurement and the technology that drives measurement is a key part of engineering. You need a way of detecting false starts. This is a picture from the World Championships when Usain Bolt got disqualified for a false start and therefore failed to do running 100 metres in 9.58 seconds. But the technology to detect false starts, pressure sensors, detectors, the way that you can actually see whether people have moved before the B of the bang at the beginning of the race. And of course, you need technology to detect the finish. So photo finish technology that allows you to pick the exact finish time. So actually, even in something where fundamentally the technology is, or the input is biological, actually there's a lot of engineering technology that allows you to achieve that kind of thing. And you can go through that sort of thought process with all of the other things that are on my list. Okay, so engineering is everywhere around you. Everything that we can do because engineers make it possible. But what is an engineer? What makes a good engineer? What is an engineer? So the next question I asked you in the survey was to tell me something about yourselves. And I gave you a list of 8 characteristics. Things like whether you felt you were good at problem solving, whether you liked to work in a team, whether you liked to lead things and organise people, whether you thought you were good communicators. And I asked you about those 8 things and said, well, tell me which of those things match you. Well, the good news is that only 6 of you said, well, actually none of these match me, which I'm quite surprised that it was even 6, but there you go. But most of them thought that the words had got something, at least some of them had got something to do with you. So the way I'm going to show you that result, the bigger the word is on there, the more of you said that you thought it was you. Okay? So lots of you said that you thought that you wanted to thought that you were good at understanding how things worked. Quite a lot of you thought you were okay at problem solving, teamwork. In terms of leadership, nearly half of you said that you were leaders who like to organise things, organise people, lead people. Okay? So, lots of you said that you like to travel, that you wanted to be part of a global culture. About just under a third of you said that you were nerdy mathematician physicists. So, okay, that's fine, you're allowed to be that. I did say go on, be honest. But quite a mixture of things that you told me about you. And then I asked you, which of these things do you think are most important for engineers? And that was quite interesting. So if I put that in the same way, then you thought that engineering was all about understanding how things work and detail with a bit of problem solving. And some of the words got so small they almost disappeared. So teamwork, teamwork, travel, communication and leadership have kind of disappeared on that chart. None of you thought that those were important things for engineers. But when I did that thing, okay, I answered a slightly different question, because I tried to do a sort of a balance of what I thought was important for an engineer. And what I said looks like that. Probably the most important things for engineers in my book are teamwork and problem solving. Any of you who have been here doing some of the things, the projects, if you looked at the projects at the back and talked to the guys who were doing the projects, the more senior projects, they will have frequently told you, we came across this problem and we found a solution. I worked with so-and-so to find a solution. I took some advice from somebody. Engineering. Our director of engineering in Rolls-Royce is very fond of saying, engineering is a team sport. It's about a month ago, we certified the new engine for the new Airbus A350 aircraft, which is going to fly next year. So how many people do you think are involved just in Rolls-Royce in creating a new aero engine? Just shout a number for me. Sorry? 80? 120? 500? Any advance? Sorry? 800? 1,000? Okay. 1,000? Okay. The official answer, and I think this might be an underestimate, is 4,000 people involved just in creating one new aero engine. That's just the engineering team, designing all the different bits, making sure it all works together. It's an incredibly complicated machine, and you have a huge team of people working together, and that's just the Rolls-Royce. That's without taking account of all the suppliers who are making the parts. 4,000 people working together. Okay? Teamwork is critical. Problem solving, I said. And actually sort of leadership, because engineers need to be driving forward technology, they need to be leading the way that the businesses are working. It's absolutely critical. And of course communication, because you can't work within a team unless you can communicate. Now that chart I filled in before you sent me the results of your thoughts about what you were like. And then I noticed something. If I put my chart of what an engineer looks like next to your chart that said what you guys look like, and I promise I didn't cheat. You put a bit more saying that actually you guys like understanding problems and understanding the way things work. But I thought those were spookily similar. I put it to you, Shells of Kings, you are budding engineers. And you have it in you to create more amazing things like those 10 things that we started with. Okay, so I want to go back to those 10 things that we started with. And I want to answer the question, which is my greatest? Which did I vote for in the survey? Because I did it to practice to make sure it worked before I sent it to you. Which is my greatest? And this may come as a bit of a surprise to you. But my greatest is online supermarkets. And I'll tell you why. Or at least I'll get you to help me tell you why. Okay. So let me tell you a story, a very brief story. November last year, I was lucky enough to be on holiday in New Zealand. And on the last day of my holiday, Saturday 24th of November, I was sat in a hotel room in Queenstown looking out at that amazing view across the lake in Queenstown with my iPad connected to nothing, and I tapped it a few dozen times and I placed an order. 44 hours later, 19,000 kilometres away, my shopping turned up. Okay? It's not my house, by the way, but for the sake of this man. But my shopping turned up. So I just want you to help me think through what technology, what amazing things were required for that to happen. Okay? So, what we're going to do, this is going to be quite useful. I'm going to give you a simple, hang on, that's not what's supposed to happen there. Ignore that. Let's see if we can make this work. There we go. Okay. So, technology sometimes gets ahead of me. So I'm going to give you a clue of a couple of technologies that we've involved. So obviously we needed the internet. So the internet may be your greatest, but it's only one small part of my greatest. And we needed a lobby, okay, because we needed something to deliver stuff. So what I'd like you to do is to shout. You're going to really need to shout, because I can hardly hear you up here, okay? I want you to shout out some technologies that you think are involved in delivering in making online supermarkets work. So give me some thoughts. We need a computer. Yeah, okay. So we'll put down a computer. Oh, I can't smell. Or maybe I can smell, but I can't smell. Computer. Okay, somebody said satellite technology. Very probably these messages were sent by satellite, absolutely. Okay, somebody in the back, yes? Oil. Why do we need oil? To drive the van, absolutely. Very good. Yeah, what else? Refrigeration, somebody said at the front. Yeah, absolutely. If the van hasn't got any refrigeration in, and you don't just need refrigeration, you need mobile refrigeration. Yes? Roads, absolutely. So that was on my list at the beginning, but it's kind of unimportant because it's just one of the things we need to do this. Okay, what else?
Manufacture of food.
Manufacture of food, absolutely. Food processing factories. Okay, what else? Preservatives. Ooh, dodgy that. We like nice fresh food in my household. No, absolutely. So food technology, we could say. Okay, what else? Electricity. Yeah, we probably need some electricity somewhere along the line to power the laptop, if nothing else. Shoes? I guess the delivery man needs some shoes. Yeah. The great thing about brainstorms is that you accept everything. Well, unless they're completely crap, you can't. What's happened to the list? That's a very good question. Okay, that's supposed to be appearing on the chart behind me. It's not. So why is that not appearing? Okay, go on. Anyway, you get the point. We could go on for ages with this. What I will do, I'll just flash up quickly the list which I came up with, if I can find the right slide. There it is. Okay, so that's the list that I came up with. Many of them that you've thought of already. Sort of a few other things. In the planes doing the air freight vegetables to get nice fresh vegetables, if I like. You need to weigh things. Of course, you need to make sure there's no horse meat in it. Lots of different technologies that you need. Okay. So that's that kind of is my justification for why I think online supermarkets are pretty amazing things. They actually bring together so many different technologies. Okay, so I want to concentrate a little bit on one of those technologies, and this is actually the technology that got me to eat my shopping, having ordered it 19,000 kilometres away. So this is a Boeing 777 aeroplane powered by two Rolls-Royce Trent 800 turbojets. Okay, and I want to talk just for the last few minutes about just one small bit of technology in a gas turbine engine. There are so many bits of amazing technology, we could go on forever. Press the right button, this will even work. So this is a slightly closer picture of a Trent 800 engine. You can sort of see the size and scale of it. These are amongst the most powerful aero engines in the world. They generate 90,000 pounds of thrust at takeoff. And just to give you a flavour of it, they're like basically they're giant vacuum cleaners that suck in 1.2 tons of air a second. Now to give you a feeling, a ton of air is what fits into a squash court. So there's probably, about 8 tons of air in here. So you suck all the air out of this ball in about 8 to 10 seconds. Okay, so before we go any further, I need to demonstrate how gas turbines work, how jet engines work. And there is, of course, a very traditional demonstration for how jet engines work, and it goes like this. So it goes like this. Here is a jet engine. There is a jet engine, not flying very far. You can do that again. You can see that you can make that very better. That one's very flat. This will be better. It's tight. There we go. That is better. Okay. So simple jet engine. What's really happening there? Well, basically, when you've got the air in the balloon and the end sealed, then the air is trapped inside the balloon. When you open the end, the air comes flying out the back. If mass comes out the back, that generates what's called an action. That creates a reaction that pushes the balloon in the opposite direction. So as the air is thrown out the back, that pushes the balloon forwards. Okay? Balloon is quite a simple example. Doesn't fly for very far or very long. How does that work when you put it into the sense of a jet engine? We describe jet engines in terms of 4 words: suck, squeeze, bang, blow. Okay? So basically, you suck a whole load of air in the front, you squeeze it down, compress it down in the middle of the engine to about 1/40th of the size that you started with, so 40 atmospheres pressure. In the middle of the engine, you ignite some fuel, that makes the air very hot, and then you blow it out the back. As you blow it out the back, you get some spare energy which you can use to suck in some more air, which you also throw out the back, and that creates the throwing back, creates the force that throws the engine forward. Okay. I want to take you right into the very middle of the engine, right into this very hottest part, just behind the combustor. Okay? This is a part out of the Trent 500 engine. It is what's called a nozzle guide vane. It sits just behind the combustion chamber. You can see in the picture, this is a model of the hot gas coming out of the combustion chamber, and this is the first part that sees that hot gas flying out the back of the combustor and turns it round the corner to make it do work in the engine. This component sees one of the most aggressive environments that you can imagine. If I show you a picture, this video is a slice through a rig test that we do. So this is the combustion chamber. You can see it filling up with fuel. Fuel will ignite in a minute. And that flame is burning at about 2,200 centigrade. Okay? Just need to stop the video before it gets too far. The flame is burning at about 2,200 centigrade. The air mixes up, and altogether, the mixed air as it's coming at the back of the combustion chamber is at around 1,700 centigrade. This part, and most of the other parts that I've got on the table here, I haven't got time to talk about all of them today, but if you want to come and talk to me about them afterwards, feel welcome. Melts at about 1,500 centigrade. So we have a problem here. We're trying to actually do work to turn the air around the corner with a metal that is in gas well above its melting temperature. The challenge is kind of like taking an ice cube and putting it in an oven at its highest setting and stopping it melting. Or, another challenge would be to take a chocolate turbine blade, like this one which I made earlier. This is genuinely a chocolate turbine blade. Okay? This was made in the same die that the model for the second turbine blade in the engine that I just showed you a picture of was made in. So that's kind of quite precious. That's the only chocolate turbine blade in the world. I describe it as less useful than a chocolate teapot for those who know how useful chocolate teapots are. So the challenge is like putting an ice cube in an oven, or indeed putting a turbine blade in front of a hairdryer. Now I don't have an oven or an ice cube here, but I do have chocolate and a hairdryer. So now I need a couple of volunteers to come and help me with an experiment? Can I have a couple of volunteers? Go on, I've got one at the back there. Go on, we'll go with you. Go on. Okay, right, a couple of volunteers. Now, I need to wind up this computer. Okay. So, right. Okay. Hi. So, what we're going to do, I need one of you to work the timer for me, and I need one of you to work the headline for me, okay? So, the timer's quite easy. If you can just basically click on start and then click it again when the chocolate breaks, okay? So, what I have here, I can't, because my turbine blade is so precious, I can't actually do the experiment with the turbine blade, but I have here a test sample. A test sample of the highest quality Sainsbury's Basics chocolate. Okay? So we're going to clamp that in there. Okay? And we're going to carefully place the drip catcher underneath. And what we're going to do first of all is we're just going to see what happens to chocolate when you put it in front of the hairdryer. Okay? So what I need you to do, sir, is to come around this side. Try not to go too far down that end because you get spattered with chocolate if you go down that end. I've done it before. Okay? So that's the on-off switch. So you need to slide that up 2 clicks. And when you slide that up 2 clicks, you need to start the timer. Okay? And then when it's finished, you need to... when it breaks, you need to turn the hairdryer off. Okay? Okay, we've got a video, so hopefully we can see what's going on in a little bit more detail for those who can't see the sample too close. Okay, so are you ready? Okay, yeah. Okay, so if you come around this side with me, then you can actually sort of see what's going on. I'm just going. Okay, so just around this side, for those of us who are close enough, we can begin to see on the top that it's actually beginning to sort of go a bit glossy looking. Material is already getting to a temperature that it's probably not totally happy at. Sometime fairly soon, if you put your hand in there, you can feel that that's probably a bit hot stuff. So you give the hair dryer, so you don't need to get too hot. So the window, you can see that colouring on the top. It's looking a little bit soft on that top corner. And hopefully, it's getting quite moving under there, isn't it? So if we kind of get on, we've got the man with the camera's going to come and have a closer look. But underneath, it's beginning to sort of punch away. Go on and on. If you can manage to get a view underneath without getting the chocolate down your camera, can you get round this side? Oh, too late. Okay, so, right, okay, guys, grab a seat up there because I'm going to leave you again in a few minutes. We'll turn that off for now. So what you can see, if Jordan can manage to get his camera in on there, you can begin to sort of see on the end of there, you can see how this kind of went quite gooey and gloopy. It sort of melted, and that's what happens to chocolate if you put it in front of a hairdryer, or indeed to turbine blades if you put them in a gas turbine and you don't look after them properly. Okay, Craig, if you can go back to the slides just for a moment. So, of course, it's worse in a gas turbine because this component just sits in the hot gas and gets hot. This is the turbine blade that sits just behind it, and that spins round as well. And because it spins round at about 10,000 revs per minute, it effectively has a load on the end of it, equivalent to hanging a heavy truck on the end, that tries to brake it. So, what better thing to do than to try this again? But this time, we'll try it with a load on the chocolate. So, what we need to do first, that says 1 minute and 5 seconds. So, we'll say we did an experiment with no load, and it took 1 minute and 5. Okay? So, the second experiment is going to be with a load on the turbine. Daisy. Okay, so guys, you can get back to your... Oops, that's broken. You guys can take that one as a souvenir.
The video back.
Yeah, if you can go back to video, thank you. Thank you, video team. Okay, so we'll just have to swap this chocolate over. Sorry, you need to go down to the flash player. Thanks. So we'll swap that over, we'll plop that back in. Okay, and we'll put a load on it this time, and we'll see what that does to how long it lasts for. Okay, so are you ready on the timer? Timer's cleared, ready to go? Yep, okay, so if you can put the hairdryer back on. Okay, so of course we're expecting this not to last as long, because it's now got just not only the temperature, which is still too high for the material, but it's also got, so can you get round this side? So we can actually sort of see what's happening on this okay. And maybe even lift it up a little bit so that you can see what's happening on this video. Okay, excellent. So now you can begin to see it's very glossy on the top, it's beginning to sort of struggle and melt a little bit. Okay, the temperature should be going, beginning to get to it a little bit, and what we normally see around about there. So, what you can see is, you're beginning to see an effect whereby you're getting a difference between the load and the no load. So, how do we cope with that? Craig, you can go back to the slides again. I told you this was quite complicated. So, the question is, how do we keep these components from melting? Because obviously, if they're going to melt, then that's a bad idea. And trust me, if I thought they were going to melt, I'd go by boat. So, question. How do you guys keep cool on a hot day? I know it's not a hot day today, not a problem really. Fundamentally, somewhere around, exactly. Okay, so fundamentally, there are sort of three things you can do. You can have some air conditioning. You can put on a hat, some kind of protection from the heat. Or you can do a bit of a fan. Blue. Well, thanks. So, air conditioning, put on a hat, give yourself a bit of a fan. Those are the things that you would do, and we do pretty much the same. So our equivalent of air conditioning is what we call convection cooling. So inside these parts, each one of these is hollow inside, and we blow cold air up the inside, pass it up and down complicated passages inside, and that essentially provides air conditioning to each individual part. Quite complicated to make, we haven't got time for that today, but just to give you an example, that is a hole. It doesn't look like it, but that's the hole that is inside that turbine. That's the solid version of the hole, of course. You make it solid and then you make it into a hole afterwards. Topic for another day. Our equivalent of fanning yourself is what we call film cooling. If I come over to Craig's camera, Jordan's camera, then what you can see in there... Oh, can we go to the video? Well, there we go. So what you can see in there's about 2,000 holes, tiny, tiny, tiny holes in there, all around the surface. It's a bit scritched and scratched, I apologise for that, but you can see all those little tiny holes. Each of those holes, out of each of those holes comes a film of slightly cooler air. It's about 600 degrees, so it's not that cool, but it's cooler air. And that provides a barrier of cold air over the surface. And then the third option is the equivalent of putting on a hat. You can put on a thermal barrier coating. So the white surface on here, we won't go back to the video, the white surface on here is a thermal barrier coating. It's a ceramic layer. It's the turbine equivalent of wearing a hat. Now I can only demonstrate one of those with my hair dryers, but we will do one more demonstration. So we'll go back to the, if we go back to the video, if you guys can get to your stations and zero the counter. So this time, what we're going to do, this is a bit complicated for you, okay? So what we're going to do, we've got a second hairdryer here, but this one's set to cool, okay? So what we're going to try and do, your challenge is to keep this chocolate intact for as long as you can, okay? So it's still going to be in front of the hot hairdryer, but what you're allowed to do, without blocking the hot flow too much, what you're allowed to do is to blow cold air into it to try and protect it from the hot air, okay? So we will pop that in there. We'll pop the load back on. It's got a bit chocolatey on the string. Okay. So that goes back on there. Okay, so what we're going to do, if you grab the cold hair dryer and turn that on ready, okay? Just make sure that is cold. Yep, okay, it's on cold. Okay, so I'm going to turn this one on. What you'll need to do is to concentrate on the bit where the highest stress is while it's been breaking. Okay? Okay, so turn it on. So we'll see how long we can manage to keep this from melting. Okay, you're not allowed to get it right in front of the nozzle because that would be cheating, but you're allowed to see what you can do to protect it. You might want to concentrate on the top because it's going to be stretching down to try and the biggest tensile force to be on the top. But we can already see we're beginning to get some of that glossy look, but you're managing to keep that away from that highest stress region, so that's kind of quite good. Obviously, one experiment we didn't do was just hanging the load on the chocolate forever. What we're going to see now, so this is already lasting longer. There we go. So that's, I think, lasted a little bit longer. Let's turn that one off. Okay, thank you guys. Grab a seat again. So, things that you can notice with this is actually this is broken in a different place. And it's broken in a different place because it's the combination of heat and load that makes it break. And actually, by changing the heat distribution, we've managed to make it break in a different place. So, the detail of the design of the way this works is absolutely fundamental to making it work. It lasted 50 seconds, so let's type that one in. So, in this particular experiment, it wasn't a lot longer, but it was a bit longer, and you can see the principle that it should work. Okay. So, those are the results that we got. We got a longer life, and clearly if we did it more carefully and with more design, we could get a longer life still. So, I've overstayed my welcome, I apologise for that, but in terms of just one of the amazing bits of technology in aerodynamics, I hope you enjoyed that demonstration. Thank you to my able helpers. Please give them a round of applause. Okay, so really, I just want to finish very quickly. I hope that I've established that we live in an amazing world, and the things that make that amazing are made possible by engineers. Engineering is a team sport, something that has to be done in groups. So just because you don't think you've got all the talents to be an engineer, don't think that that means you can't contribute a good deal. It's about working together to solve problems. If we had longer, we could work out how to make chocolate last longer in front of hair dryers. I guess most fundamentally of all, I could not have imagined online supermarkets when I was sat where you are. You guys may be able to imagine the things that you might be talking about in 30 years' time. I hope you can, because the future is limited only by your knowledge. Thank you very much.